Hey guys, my name is Pedram, and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Part 28, Decision Trees. Let's start with terminologies. So, decision trees are a sequence of simple questions seeking to partition the dataset into homogeneous groups. They can be applied both to classification problems or to regression problems. Let's look at an example for a classification problem. So imagine we have two features, x1 and x2, right? And we are dealing with two classes, blue versus red. So starting with asking some simple questions from the top of the tree, let's say for the sake of argument, we start with feature x1, and we said if x1 is greater than s1, this is our split number one, then if the answer is true, go to the right, go to region number one. So this is our region number one. If the answer is false, let's ask some other questions. Now let's look into x2 and see if x2 is greater than the split number two, right? If it is greater than number two, go to region two. If it is less than s2, go to region three, right? So this is how simply a decision tree is going over basically some simple questions and classify the observations into two classes, blue versus red. Now, how does this classification happen? For example, look at region number one. So in region number one, so if you have a test observation, let's use green. If you have a test observation here, what is going to be the class of this test observation? The answer is blue, right? So region number one is going to be classified as blue. Why? Because we can assign probabilities to classes. What's the probability that the observation is blue? So how many observations do we have? We have 10 observations and 9 of them are blue. So the probability is going to be 9/10 of blue, right? So blue with the probability of 9/10. So right off the bat, you should realize that the outcomes for decision tree classifications can be probabilities, just like logistic regression or auto models that generated probability outcomes like KNN. However, this is unlike the SVM. In SVM, we saw that the outputs are not probabilities. Okay, so region number one, the output is going to be blue. Region number two, what is the output? It's going to be blue again. Again, we can assign some probabilities. And for region number three, the output is going to be red, or the probability of blue is going to be smaller, right? Okay, so this is how the classification is done using a decision tree. As you can see, the steps are very straightforward. This is a very, very interpretable model because you can exactly see what's happening inside the tree. You can interpret them perfectly. And it's a non-parametric model. It means that we are not imposing any functional form to the model. We are not assuming any distribution for the features, and so it's going to be non-parametric. Decision trees are supervised machine learning algorithms that can be applied to both regression and classification. So we already said that decision trees are very simple and straightforward to work with. They are interpretable, they have lots of good characteristics, lots of advantages, like they can handle categorical data very well, you don't need to do pre-process the data. So it has lots of advantages. But at the same time, these models, the decision trees alone, are not that powerful when it comes to the performance, right? Both for classification and regression, usually the performance of a single decision tree is not going to be that satisfying. So for that reason, we're going to work with the variation of decision trees down the road. We're going to basically look at a bunch of those trees together. We're make an ensemble method, and then to maybe make predictions using those ensemble methods is going to do a better job, right? So for this episode, we're going to start with decision trees. We talked about advantages and disadvantages. We basically cover some basic terminologies. And then later on, we're going to talk about the idea of now let's combine these decision trees. Let's use bagging and random forest. And finally, we're going to talk about boosting. So we're going to cover these topics in the future episodes. But for now, let's dig into more details of the decision trees. Okay, so let's do it. In this episode, part 28, we start with decision tree definitions. And we're going to go over something which is called decision tree criteria. This is actually the heart of decision tree algorithm. At the heart of the algorithm, we need to answer two questions. What feature to start with and where to put the split. In order to answer these questions, we need to come up with some criteria. For regression, we're going to use MSE, mean squared error. For classification, we're going to use some measures that we call them the impurity measures. So we're going to discuss the details in this episode. In the next episode, we're going to go over decision tree classification and regression models. Part 30, we're going to talk about pruning a tree. Let's say we have a bushy tree and you want to start pruning it down back. Okay. We're going to cover the hyperparameters in part 30 as well. And finally, we're going to conclude our journey of decision tree models by going over pros and cons and applications in finance. So what are decision trees? Decision trees are machine learning algorithms that progressively divide dataset into smaller data groups based on a descriptive feature, right? So we have a bunch of features, x1, x2, x3. So based on those features, it's going to divide the data sets progressively until they reach to sets that are small enough to be described by some label, right? At the end of the day, so that label can be quantitative or qualitative. If it is qualitative, it's decision tree classification. If it is quantitative, it's decision tree regression. We're going to see much of more examples, and it should make more sense. Decision trees apply a top-down approach, right? Because we start at the very top of the tree and then we come down. So this is a top-down approach to data, trying to group and label observations that are similar to each other. So these are key terms, right? So basically, you want to label them based on some measure of similarities. So let's look at this very simple example. Imagine we are looking at height versus weight, and there are two classes, male and female. So let's say blue is male and red is female. Basically, you want to say, okay, so if I have two features, two descriptive features, namely height and weight, then based on those features, what is going to be the outcome of a new person, right? So for example, if we have a new individual in the data set, let's use green. So this new individual, we want to see based on these features, height and weight, what is going to be the gender? Is it going to be male or female, right? So remember those two important questions in decision tree models. What feature to start with, where to put the split? I want you to think about this question. So between height and weight, what feature do you think is the better one to start with? Okay, so maybe it's better to start with height, right? If you start with height, so you're going to divide the data into two subsets. Let's call them region 1 and region, for now, let's call it region 2, okay? So visually, if you look at region 1, maybe we are satisfied, right? So we are satisfied with region 1 because you may think that, okay, look at the number of misclassifications here. It's mostly blue, so I have a good region, you know, that they are similar to each other. The observations are similar enough to each other. So if you are satisfied with region number 1, we're going to say that, okay, let's keep it that way. For region number 2, however, there are lots of misclassifications, right? There are lots of blues and red. So we need to go down the tree. So let's say this way, we need to go down the tree. So what do? What feature should, again, we have to answer those two questions. What feature to start with, where to put the split. So in region 2, it doesn't make sense to start with height anymore because, height is all around the place in terms of male versus female. But look at weight. If I have something like this is going to do a relatively decent job, right? So let's look into that. We're going to divide region 2 in two subgroups. So let's use this split, and we're going to end up with two new regions, right? So basically, what are we doing? We're answering these simple questions. If height is larger than 6 feet, yes, male. So if male, we are in region 1. So let me actually. Then if height is less than 6 feet, or if it is not greater than 6, if the answer is no, we go to the left and then we look at the weight. If weight is greater than 180 pounds, then it's male. So we are in region 2. So let's call it region 2. And then finally, otherwise, we are in region 3. So this is region 3. Okay. Now, for whatever reason, let's assume that we're satisfied with what we see in terms of purity of the regions. Look at region 1, region 2, and region 3. So we're going to call it a day. Say, okay, hey algorithm, stop here. I'm satisfied with the regions, right? So then we say, okay, now let's assign some numbers, some probabilities. Imagine you're going to predict if the outcome is going to be male or female, right? So if the outcome is male, then we can assign some probabilities to this outcome. So what is the probability of male in region 1? Whatever it is. So for example, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 observations. So 8 out of 9 is going to be the probability of blue. So this region is going to be blue. We can assign probabilities as well. The same is story for region 2 and region 3. So region 2 is going to be classified as blue, and region 3 is going to be classified as red, which is female. Okay, so we already know them. Blue is male and red is female. Okay, now let's talk about the details, right? So how did we decide that this region number 1 is satisfying? So how can we quantify these decisions, right? So visually it was easy for us, but for the computer, and let's say if we have some problem with very high dimension, it's not as straightforward, that we don't have the luxury to visualize it, right? So let's see what ingredients do we need to understand first. Then based on those ingredients, we're going to discuss about the details of decision tree regression and decision tree classification. Decision trees definitions. So when the target variable consists of real numbers, that's going to be a decision tree regression, right? So what are the examples? Imagine your target variable is wage, consumption, stock price, stock market returns, you name it, right? These are examples of real numbers. And when the target variable is categorical, you're going to deal with a decision tree classification. For example, the target variable can be 2 classes, default, no default, pass, fail, accepting a loan, rejecting a loan. Or it can be more than 2 classes, like say in the stock market you want to bet on direction, right? So buy, sell, hold, things like that. So what are the other terminologies? Starting with the top of the tree, we have root node. So here we start a tree by its root node, right? And root node is just the beginning of a tree. Then we start going down the tree. So what is the process of a splitting? So splitting is simply dividing a node into 2 or more subnodes, right? So here, this is what we call splitting. Then in order to connect these nodes, we need to use something called branch. So the branch is going to connect these nodes. So we'll connect one node to another. Then the next concept is decision node. Decision node, or we also call it internal node. It is internal node because it's just in the middle of the tree. And we're going to make decision in these nodes, right? So we made a decision in root node as well. So for example, if x1 is greater than split 1, yes, go to the right, no, go to the left. So this is also a decision node, but because it's at the top of the tree, we call it root node. If it is in the middle of the tree, we call it internal node, but regardless, we're making a decision here. So here's internal node or decision node, decision node, decision node. Then the next one is leaf node or terminal node. So each branch is going to finish at a terminal node, right? So the terminal node is basically the node that it's at the end of the decision tree where it cannot be split into further subnodes, right? So in this example, we are going to have 5 terminal nodes, okay? And we stop here, for example, because of a couple of reasons. Maybe we are adding stopping criteria to the model. We want the model to stop here. We're going to talk about the details later on. Or simply maybe there is not enough observations down the road in this specific part of the data, right? Okay, then the next concept is subtree. Subtree is basically a part of the entire decision tree, and which starts with a node and ends with a terminal node, right? So for example, this is a subtree, and this is a subtree. What about this one? So let me just erase this one. What about this one? Is this a subtree? No, right? Because it's not ending with a terminal node. How about this one? This is going to be a subtree, right? Okay, then another concept is called depth of a tree, or we can simply call it level, and that's defined as the length of the longest path from the root to a leaf, right? So look at this tree. Where's the longest path from root to leaf? Maybe this one, right? So we go Here we can either go to the left or right. So let's go to the left. So this is the longest path. And what is the level or depth of this path? So as you can see, there is 1, 2, and 3 levels. So the depth of this tree is going to be 3. Then the final concept is pruning. And pruning basically means that removing a subnode from the tree, right? And we're going to remove a subnode of a tree. And if we do that, it's going to remove the leaf as well. We replace everything by a terminal node. So for example, look at this one. Let me use red. Look at this part of the tree. Imagine I want to remove this internal node. If I remove that, so the entire thing, the entire subtree at this region is going to become a terminal node, right? Terminal node or leaf node. So this concept is called pruning. And the idea is applied to, for example, you have a very bushy tree and it's overfitting the data and you want to prune it back. You want to make it less complex. All right, so we're going to talk about all these details later on, but this is just a simple terminology. Okay, decision trees criteria. So at the heart of decision tree algorithm, we are answering 2 questions. What feature to start with, where to put the split. And in order to answer this question, we have to figure out which split adds the most information gain to the model, right? And by most information gain, we mean you can think of it as maximum purity. Which split is going to generate the maximum purity among the classes, or minimum impurity. These are all alternative terms that we can use, right? So let's look at an example. So this is a very balanced, exaggerated example. We have 20 observations, 10 of them are blue, 10 of them are red. Let's say we have 2 features, x1 and x2, and it's very, very balanced, right? So let's look at some splits. So if you look at this data set, most probably it is obvious that which one is a better split, what feature to start with. But let's just for fun, let's look at an exercise. So imagine we start with this split, right? So we're starting with feature number 1 and put the split here. Do you think that it's a good split? Well, actually it's going to be one of the worst one, right? Because why? You can see the maximum impurity here. We have region 1, region 2. Do you see the maximum impurity? We wanted to minimize the impurity, not maximize it, right? So this is not going to work. What about this split? Well, this split is going to be actually a perfect answer here, right? Because what is purity here? 100%. What is purity here? 100%. So the impurity is 0 if I use this split, right? So how can we quantify these things? In order to quantify this level of satisfaction, so let's say impurity, and etc., we need to look at some statistics, right? If we are dealing with a regression model, we look at our old friend MSE, this is mean squared error. We can also look at RSS, residual sum square. So basically a split is a good split if it is reducing the MSE or reducing the RSS more, right? So for regression, it's very straightforward. For classification, however, we are going to work with more than one statistic, so more than one measure. We are going to work with error rate, entropy, and gini index. So error rate is something that we're all familiar with, the number of misclassifications. So for example, here, if I use a split green, what is the error rate here? 50%. What is the error rate here? 50%. If I use the red split, what is the error rate here? 0. What is the error rate here? 0. So you already know that you want to minimize this, the error rate, right? For entropy and Gini, the story is the same. These are some measures that control how a decision tree decides to split the data, right? And all of them are measure of impurity. I'm going to talk about the details of entropy and Gini index, but remember, at the big level, we want to minimize these things. We want to minimize error rate. We want to minimize entropy or Gini index. And down the road, you will see that these entropy and Gini index are going to be a better measure compared to error rate. And from now on, we're going to work with either entropy or Gini index. In the next slide, I'm going to explain why. So what is entropy? What is Gini index? We know that they are both measure of impurity, right? But let's see what is the difference between the two. Entropy is going to measure the impurity or randomness or uncertainty in the data points, right? So for example, in the previous one, if we use the green split, the uncertainty is going to be larger, right? The randomness is going to be higher. The impurity is going to be higher. Gini index, on the other hand, measures how often a randomly chosen element would be incorrectly labeled, right? Again, in the previous example, if you use the green split, the answer is 50%, right? Know how often a randomly chosen element would be incorrectly labeled. Okay, so in either case, we know that a number closer to 0 is better. Why? Because 0 expresses all the elements belong to a specified class, to a pure class. So we like these metrics, the entropy, Gini index, to be as close as possible to 0, because that's a sign that you're getting a more pure classes. And so in the previous example, if you use the red split, both the entropy and Gini were 0. Okay, so let's look at the formula for either of them. And later on in the course, I'm going to work with a numerical example and cover all the combinations of how we can calculate entropy and Gini, at least for once. And then afterward, we're going to just trust computer, and the computer is going to do the calculation for us, right? So what is entropy? Entropy is a function of the p, this is probability of each class, multiply log of p, right? And we add over all the classes that are available. So this is, I want you to just focus on the big picture. And Gini is simply equal to 1 minus the probability of classes to the power of 2, and then adding them together. So in either case, look at that. If the probability of a class is close to 1, if the class is pure, what will happen to entropy? So look at that. Here we plug 1, and we plug the log of the 1. What is log of 1? It's going to be 0 to add any base, right? So 1 multiplies 0, 0. What about this one? The probability of each class, if the class is 1, so 1 to the power of 2 is 1, 1 minus 1, 0. So as you can see, if the class is pure, both entropy and Gini are going to go toward 0. If the class is 100% impure, so if the probability, for example, goes to 0, the same story. Both, if you do the math, both the entropy and Gini are going to go towards 0. Okay, so let me give you an example that hopefully is going to shed light in terms of how to distinguish entropy, how actually calculate entropy and Gini index. Imagine you're flipping a coin, right? And you're flipping a fair coin. That means that the probability of tail is going to be equal to the probability of head is going to be 50%. When do you get the maximum uncertainty when you're flipping a coin? You get the maximum uncertainty if the coin is a fair coin, right? Basically, if the probability is 50%. So if the probability is 50%, then you get the max uncertainty. You get the max amount for entropy, your max amount for Gini index, the max amount for misclassification, right? Or the error rate. So basically, in this simple example, if probability is 50%, you're here, we get the maximum value for entropy, Gini, and misclassification error, right? So this gray curve is what we call a Shannon entropy. The Shannon entropy in the formula is going to use log to the base of 2. Okay, so if you do the math, when you just replace 0.5, log of 0.5 plus 0.5 log of 0.5, you're going to get minus 0.5 plus minus 0.5, so minus 1, multiply minus, you're going to get 1, right? So that's why you get 1 if the probability is 0, if the probability is 50%. But however, for other metrics, for Gini, you're going to get 0.5 if you just plug probability is 0.5 here. So 1 minus 0.5 to the power of 2 plus 0.5 to the power of 2. So you get basically 0.5. Okay. So for misclassification, the same story. What is the probability of making the error? So it's going to be 50% if you're flipping a coin, right? So that's why we are going to report this number as 0.5, and we're going to work with a scaled version of Shannon entropy. So this is the Shannon entropy when the log is in base 2. If we just transform the log to base natural log, we're going to scale it from 1 to 0.5 for the maximum uncertainty, right? So this is, now we can compare these impurity measures a lot easier, right? I can compare, and by the way, we call this cross entropy. Cross entropy. So I can compare cross entropy, Gini, and misclassification error a lot easier. So now I want you to focus on the bottom part of this chart and look at that. When the classes are pure or impure, which one is more sensitive to basically changes in probabilities or more sensitive to purities? Look at that. It seems to me that the red curve is more sensitive than the green one, and that's more sensitive than the blue one. So entropy is going to be more sensitive than Gini, and Gini is going to be more sensitive than error rate. In practice, entropy and Gini are very close, they are very close to each other, and that's why we usually prefer them to misclassification error. Okay, so that's all we needed in terms of basic terminologies to be able to understand decision tree models down the road. So I hope you get the basic concept, and with that, I'll see you in the next one.